Thanks, Santosh. I'm Dave Blei from Columbia, Computer Science and Statistics, and I'm going to talk about scaling and generalizing approximate Bayesian inference. Please interrupt with questions. This talk is really long, so I'm happy to not get through the whole thing. Is there a question already? Okay. Okay. So first I just want to show you some pictures of some results that we've gotten using the kinds of algorithms I'm going to talk about today. This is an overlapping community structure discovered in a big 3.7 million node network of US patents. This is a picture that we'll get back to later of topics, word patterns that were uncovered from a big collection of 1.8 million articles from the New York Times. This is a population genetics analysis of discovering ancestral populations in a big collection of 2 billion genetic measurements. This is the Pritchard-Stevens-Donnelly model, if you're familiar with that, the admixture model. And this is a neuroscience analysis of a massive fMRI data set where we're trying to find significant locations of brain activity and how they are correlated with each other under different stimuli. And this is an analysis of 1.7 million taxi trajectories in Portugal. It's an important problem. And this is done in a I don't know why this keeps happening. Done in a probabilistic programming system called STAN. Hopefully this will stop blinking if I screw this in. Okay. So all of those pictures that I went through quickly are implementations of what I like to call the probabilistic pipeline, where it's really very common, it's so common we don't even talk about it, where we take our knowledge of a domain and a question we want to ask of the domain, we use it to form a probability model, make assumptions about the data that involves hidden and observed quantities. Then we square the model with our data to discover the hidden quantities given the observations. That's the posterior inference problem. It's the focus of today's talk. And then from those discovered patterns, we then form predictions and explore the data set in question. And I like this picture because doing customized data analysis is important in many areas of science and industry. And this pipeline separates these key activities of making assumptions about the data, uncovering patterns. I don't know what's going on here. Maybe I'm going to try a different dongle. They have many dongles here in Berkeley. I can try this one.
Okay.
It's the HDMI one. It's blinking more, yeah.
Okay. I think this one, I think,
all right.
is a little more reliable.
All right. I just don't want a seizure, you know.
You might still need to plugged in for the.
I won't use the. It's okay. I'll skip the remote. This doesn't even fit in the thing. Oh, there we go. Now oh, there it goes. Okay, good. So, back to this I'm not sure what's wrong. Well, anyway, you can kind of see the slide before it turns off. This separates these key activities, and it makes it easy to solve statistics problems collaboratively, because somebody can walk into your office with a big data set and a question they want to answer about it and draw a graphical model on your whiteboard, and then they can leave and you can figure out how to use their graphical model to infer the hidden variables given the observations, and then call them back and take a look at their data. Now you can see from this picture that the key, okay. Maybe, do you think it's the computer? It's good. This is the test run for today's session.
Can we load your presentation on another laptop?
Yeah, sure.
Okay, I've got one here.
People have questions meanwhile?
Yeah. Let me put it on a, I have like a zip drive I can put it on. That's weird. Is that right? I had so much tutorial fluff in this talk that I'll just skip it all and we can get right to the actual talk. So this isn't going to cost us any time. Can I use this too?
Yep.
Awesome. All right. Thanks for being patient. Okay. Posterior inference is the key problem. How do you condition on data using your complicated assumptions and uncover the hidden structure? Okay. So let's get into it quickly. Probabilistic machine learning. What's this all about? It's about probabilistic machine learning. A probabilistic model is a joint distribution of hidden variables and observations x. We wrote that down, P of z and x. This inference problem where this is where we make our assumptions about the data. The inference problem is where we condition on our observed data and infer the hidden structure that we imagined lived in that data from it. And inference about the unknowns comes through the posterior distribution. This is the conditional distribution of the hidden variables given the observations, P of z given x in this generic notation, which many of you know is simply the joint divided by the marginal probability of what we're conditioning on, also called the evidence. Now the issue is that for most interesting models, this denominator is not tractable to compute. This is a computational challenge to machine learning. And so we have to appeal to approximate posterior inference. So today, I'm going to talk about variational inference. Later, you'll hear about MCMC and how to scale MCMC up. This is about variational inference. The basic idea behind variational inference, so all of those pictures I showed you were a solution to this posterior inference problem. How do I get P of z given x under different ways of assuming what x is and how what z is and how z interacts to produce my data x. And what variational inference does is turns that inference problem into an optimization problem. And so here's the idea. This is P of z given x. This is what we want, the posterior distribution of the hidden variables given the observations. And what we do is we posit what's called a variational family. This is a family of distributions over the hidden variables q that's indexed by some parameter nu. All right, so I drew that here as an ellipse. This is, in every point in this ellipse is a different realization of this variational family, a different distribution over z. Okay? You start with some particular realization of that distribution, nu init, and what you do is you optimize, you adjust those parameters to find nu star, the particular variational distribution that is closest to the posterior that you care about, the target. Okay, and so that closeness is measured in KL divergence, KL between Q and P. Okay, you can use other divergences too, but here we're going to focus on KL divergence. All right, so this picture is all you need to know about variational inference. I have what I care about. I have a family of distributions. It's got a free parameter, and then I optimize that free parameter to find the one that's close to the thing I care about. And then I use nu star as a proxy. I use Q of Z given nu star as a proxy for the exact posterior that I can't actually compute. Okay, and in case you're interested, other divergences link to other kinds of variational algorithms like expectation propagation, belief propagation, and so on. All right, so here's another picture to show you this in practice. This is a common example, the mixture of Gaussians. Okay, and so it's hard to see here, but what we have here is data that's drawn from a mixture of Gaussians. You can see these little clouds of data points here. And what we're going to do is try to approximate the posterior distribution of the cluster means given this under a mixture of Gaussians model with this data. All right, and that turns out to be an intractable posterior inference problem if you place priors on those cluster means and so on. And what we're plotting here with these contours is the posterior predictive distribution of the next data point given the observations. And as variational inference proceeds, as we take our approximate posterior and get closer and closer to the to nu star, to the one closest to the posterior, you can see that that posterior predictive distribution gets better and better at capturing the distribution of the data. And here's a picture of the KL divergence getting smaller. It's the same as something called the evidence lower bound getting bigger. We'll talk about that in a bit. Here's a picture of that KL divergence getting smaller as we run this algorithm. Okay, so this picture is the picture of taking this path to find a good approximate posterior. Okay. Because of the technical difficulties we had earlier, I'm going to skip the history of variational inference, but I'm happy to talk about it at the end. I'm trying to make up for time. So, in summary, for this background, variational inference approximates difficult quantities from complicated probabilistic models by turning the calculation about that model into an optimization. Okay, that's what variational means. And the theme of this talk is that stochastic optimization makes variational inference better. One, it lets us scale it up to massive data to approximate posteriors for very large data sets. Two, it lets us generalize VI easily to a wide class of models. And three, it lets us apply expressive variational families and something called amortized inference, which I'll mention at the very end. Okay, so that's the idea. Stochastic variational inference turns inference into optimization, and stochastic optimization takes us to a new place in terms of variational inference. Okay. So first I want to talk about mean field variational inference, which is the simplest variational inference algorithm, and stochastic variational inference. Mean field variational inference casts Bayesian computation as a simple optimization, and stochastic variational inference scales to massive data, as I mentioned. All right, so the motivating example we're going to use is topic models. Topic models are a class of probabilistic models of text that are used to form parsimonious representations of the documents so that we can do things like navigate and explore and understand what a big collection of documents is about. So the basic idea is that you ingest a big collection of text and you spit out some kind of interpretable hidden structure in those texts that lets you do things with them. Okay? Topic models are a good example for variational inference because there's a very simple topic model, latent Dirichlet allocation, that I'll talk about now. And it's kind of the simplest complicated example of a probability model that requires something like variational inference. Okay, so what's the idea behind latent Dirichlet allocation, just so we have a model in hand that we can work with? The idea is that a document exhibits multiple topics. Okay, so here's a document from Science magazine, and it's about determining the number of genes that an organism needs to survive in the evolutionary sense. And what we're doing with this document is highlighting different words with different colors. So words like numbers, computer, predictions, analysis, these words are highlighted in blue. These are words about data analysis. Words like sequence, genome, genetic are highlighted in yellow. These are words about genetics. And words like organism, life, survive, words about evolutionary biology, are highlighted in pink. And so the idea behind latent Dirichlet allocation is that if you picked a document out of Science magazine, it would blend different topics. This one blends data analysis, genetics, and evolutionary biology. And different articles blend different topics. And the goal of the model is to take in a big unannotated collection of text and discover what those topics are. That's the idea. Okay? Now what we're going to do, what we did, was embed this intuition into a probabilistic model. Okay, and so I worked on this like many years ago here in Berkeley with Mike Jordan and Andrew Ng. So the model here looks like this. Every topic is a distribution over terms. Okay, so here are some made-up topics. This one has words like brain and neuron with high probability. This has words like data and number with high probability, and so on. And then for each document, we imagine it's modeled as a mixture of these corpus-wide topics. Okay, so this document then is generated by first choosing a distribution over those topics. Okay, so here I chose the distribution that has data, the data analysis topic, the evolutionary biology topic, and the genetics topic. And then for each word, I choose one of these colored buttons from this distribution. Here I chose the blue button. And then I look up the corresponding topic and I choose the word from that topic. Okay, and this is how LDA imagines documents are written. We draw a distribution over topics, and then for each word we're going to write, we choose a topic and then choose what word it's going to be. Okay, then we turn the page of science, and we're going to write a new article. We're going to choose a new distribution over topics. So the next article might be about evolutionary biology and neuroscience, and we're going to choose its words from those topics. Okay, so you can see this is just like a mixture of Gaussians, but it's a mixture of multinomials. It's different than a typical mixture because I have many, many, many different groups of data, right? I have many documents. Each one's a collection of words. Each one comes from a mixture model where the mixture proportions are unique for each document, but the mixture components are shared across the whole collection. Okay, in statistics, that's called a mixed membership model. Okay, so that's the model. That's our knowledge of the world and the assumptions we're making about it, that documents exhibit multiple topics. Now, here you see what posterior inference is, right? So we only get to observe a big stack of documents. And so what we want to do is calculate the posterior, the conditional distribution of all of this fancy hidden structure that we imagined lived in our collection but that we don't have, conditioned on our observed data. Okay? But of course the rub is we have, you know, we're here in Northern California. We have billions of text documents, and we want to condition on billions of text documents and get out all of these inferences about these hidden variables. All right, and so that's the challenge. The challenge is how do we do this kind of posterior inference at scale? Okay, so as I'm sure you all know, in machine learning, we like to represent our probability models as graphical models. Okay, this is the directed graphical model of LDA, latent Dirichlet allocation. And graphical models are nice because they encode the assumptions we're making about the data as a factorization of a joint distribution of the hidden and observed random variables. This picture, this graph, connects the assumptions that we're making about the data to algorithms for computing with the data, and it defines that posterior distribution that we care about. Okay, and so to read this picture, in case you're unfamiliar, a node is a random variable. An edge denotes a dependence between two random variables. A shaded node is an observation, and an unshaded node is a hidden variable. So that imaginary generative process I described for LDA can be read off of this picture, where there's one more piece of notation. A plate is a rectangle, denotes replication. Okay, so in this picture, we first have our k topics, say 100 topics. Each beta k is a distribution over terms. And then for each document in the collection, I choose a set of topic proportions theta from a distribution over topics. And then for each word, I choose a colored button z, and then I choose a word from the corresponding topic. Okay, so you can kind of see how that algorithm for generating data is encoded in this picture, right? And then that the nth word of the dth document depends on the button that it is associated with, and of course on the topics in order to look up the distribution over terms attached to that button. Okay, but what's nice about this is that this really is a formal mathematical object that we can manipulate and work with to develop the algorithms we need to calculate the conditional distribution of all of these hidden variables given the observations.
any of these
Moses.
components be replaced with worst-case assumptions? And would that change things?
Can any of these arrows be replaced with worst-case assumptions? That's a good question. I haven't thought about that. I now would like to. I wish this talk were over and I could go think about it now. That's a great question. Yeah, so we in statistics and in machine learning, probabilistic machine learning, we typically write these things down and treat these arrows as defining the process, the mechanics by which I get W given beta. But thinking about there being a range of mechanics there is very interesting. Yeah. Okay. So this defines a joint, P of beta, theta, Z, and W. But of course what we're after is the posterior, P of beta, theta, and Z given W. That posterior is the joint divided by the marginal distribution of the observations. That marginal distribution is simply the joint with everything else marginalized out. Okay? And the issue with many interesting models, with all interesting models, is that we can't calculate that denominator, P of W. And that's why we need approximate inference. With approximate inference, when we scale, we get these kinds of topics. So taking those assumptions, 1.8 million articles from the New York Times, this is how I got this picture of meaningful patterns of words in these millions of articles of the New York Times. Okay, so here's one: art, museum, show, gallery, works, artists, street, paintings, exhibition, and so on. Okay, and so how did we get this picture? We set up that model. We ingested 2 million articles from the New York Times. We asked for the posterior distribution of the topics given 2 million articles of the New York Times. And then we just visualized the most frequent words from these topics for each one in order to see what the New York Times is about. Okay, so how did we get there? How do we get that algorithm? So what I want to do now is define a generic class of models that LDA is an instance of, describe the classical mean field variational inference algorithm for that big class of models. So I skipped the history, but variational inference came from ideas from statistical physics that were then ported into probabilistic models kind of independently by people like David Mackay and Jeff Hinton and Mike Jordan. And I'm going to derive the classical algorithm for this big class of models based on that work. And then derive stochastic variational inference, which is how we scale this classical algorithm up to very large data sets. Okay, so first, conditionally conjugate models. This is a generic model. I have what are called global hidden variables beta, local hidden variables zi, and observations xi. All right, and you can see the joint distribution here is the probability of beta times, conditionally independent of beta, the probability of the local and observation given beta. Okay, the observations are x1 through n. Local variables are z, global variables are beta. And the difference between a global variable and a local variable is that the ith data point only depends on its local hidden variable and the global hidden variables. Okay, so you write down your favorite probability model, you can take a look and see what things are conditionally independent, and that helps you divide up your latent variables into local and global. Okay, the goal in this generic model is to calculate the probability of beta and z given x. So some jargon. A complete conditional is the conditional distribution of a latent variable given all of the observations and all of the other latent variables. All right, that's what we call a complete conditional. And we're going to assume that each complete conditional is in the exponential family. Okay, so for example, here's p of beta given z and x. That's a latent variable given all the observations and all the other latent variables. And when I say we're assuming it's in the exponential family, that means it can be written down in this form. Okay, so it's basically, what's important here is that it's proportional to an exponentiated dot product between some parameter, here it's called eta sub g, and the variable itself. Okay, and this exponential family describes many of the distributions that you know: Gaussian, Poisson, Gamma, Bernoulli, and so on. They're all in the exponential family. All right, and so what you can notice here is that we're assuming this is in the exponential family, and its parameter, that's what's called the natural parameter, is of course a function of what we're conditioning on. Okay, so beta given z and x is in the exponential family with parameter eta g, z, and x. And the local variable z, given all of the other variables and all the other observations, first is independent of everything except the global variables and its observation, the ith observation. That comes from this graphical model. And it too is in an exponential family whose natural parameter depends on what we condition on. Okay, so this is an assumption we're making in this big class of models. Now, for the global hidden variable, when we assume that its complete conditional comes from an exponential family, what that means is that it comes from, it's got a conjugate relationship to the pair of zi and xi. Okay? And in particular, we can then write the global natural parameter as some hyperparameter alpha plus a sum of a function of these hidden variables and observations. Okay, and what this describes is, again, common relationships that you know, like the relationship between a Gaussian mean and a Gaussian random variable, the relationship between a beta prior on bias of a coin and coin flips, the relationship between a Dirichlet and a multinomial. These all can be written in this way, where the original distributions have this natural exponential family form, and the conditional distribution of, say, the bias of the coin has a form of a hyperparameter plus a sum of some sufficient statistics of observations and hidden variables. Okay, any questions about this setup? So this setup describes many models. Okay, Bayesian mixture models, factorial models, matrix factorization models like factor analysis, PCA, CCA, Bayesian nonparametric models like Dirichlet process mixtures and hierarchical Dirichlet process mixtures, certain multi-level regression models like linear regression, probit regression, stochastic block models for community detection, mixed membership models like LDA, and other variants of mixed membership models. Okay, so they can all be shoehorned into this setup. Okay, so in the setup, let's get back to our original goal of approximating the posterior distribution of all the hidden variables given the observations. And what that looks like is minimizing the KL divergence between Q of beta and z with some free parameters nu, and the posterior P of beta and z given x. Okay, and just keep in mind, we are now simultaneously doing variational inference for all of these models. Question?
Is there a natural way to see that it's the KL divergence you want from the assumptions that you made?
Good question. It's not. So the KL divergence is chosen because it makes this optimization problem possible. But one of the open areas in variational inference is to, one, recognize all of the bad properties that the KL divergence has when using it in this context, and there are many. And then two, finding alternative divergences that we can still work with, or alternative optimization methods to alleviate those bad properties. That's a good question. But yeah, so we're going to pick KL and KLQP because it's going to make life easy. Okay, so that's our goal, to find new star. And in variational inference, if you start reading papers about this field, you will hardly ever see the KL divergence. Rather, you're going to see this term called the evidence lower bound, the ELBO. It's coined by John McAuliffe in a paper. And the evidence lower bound looks like this. It's an objective function as a function of the variational parameters. And it's the expected log complete likelihood of all the hidden variables and the observations, plus the entropy of the variational distribution. Okay, this is the ELBO. And the KL is intractable to calculate exactly. The ELBO is equivalent, maximizing the ELBO is equivalent to minimizing the KL. It differs from the KL by a constant, which is in fact that log P of x term that we can't calculate anyway. The ELBO also happens to be a lower bound on the evidence, log P of x. Okay, now KL divergence is intuitive. We know it as a distance between distributions, or not a real distance, but a type of measure of closeness of two distributions. The ELBO is interesting to look at in and of itself. So it trades off two terms. The first term, right, if you just stare at this term, then if I'm maximizing the ELBO, then I want variational parameters that capture the likelihood of the data that I observed, right? If you divide this up into log p of beta plus log p of z plus log p of x given beta and z, then that last term will dominate, and this will want Q to place its mass on the configurations of beta and z that have high likelihood for the observations. Okay? So this is like finding a map estimate. If I only optimize this term, I'm finding a map estimate. But this entropy term, of course, prefers Q to be diffuse, prefers Q to spread its mass around different configurations of the latent variables. And so the elbow is explicitly trading off these two terms. And this is what we're optimizing when we do variational inference. Now, one caveat, the elbow is not convex. Okay, so this is seems to be a theme in machine learning these days. Let's not worry about not convex objective functions. They do a good job. Okay, and the elbow is going to be one of those, and this is also an interesting open area of research in variational inference. Can we characterize the elbow? Can we understand why optimization seems possible? What kind of optimums are we getting, and so on? Okay, so we've set up our problem a little more formally. We have a big class of models. We have an objective function, but we need to specify the form of Q of beta and z. This is where the mean field assumption comes in. So we need to set up, in other words, what these variational parameters are that I'm optimizing. And we're going to use what's called the mean field family, which is a fully factorized family. It says that every variable, beta and zi, for each observation, comes from its own distribution with its own variational parameter. All right, so here we denote Q of beta has variational parameter lambda, Q of zi has variational parameter phi. All right? Now, if you're a statistician, this looks really crazy, right? This is just a bunch of disconnected random variables. There's nothing connects these to each other or to anything else. Okay, everything is just free. And that's true. So this is a completely free family of distributions where every variable has its own marginal distribution and every variable is independent of every other variable. But the idea, of course, is that through the elbow or the KL divergence, we are connecting this distribution to the posterior that we care about. All right, and so what we're doing when we do variational inference is tweaking these knobs, turning the knobs of these marginal distributions of each of these variables so that the corresponding factorized distribution is somehow close to the posterior here. So you can immediately see that we will never capture posterior correlation this way, right? We can't tell you what the posterior correlation is between two variables because we can't capture it in Q, but we can capture very complicated collections of marginal distributions of each hidden variable. All right, so topic 1 can be about neuroscience, topic 2 can be about data analysis, topic 3 can be about genetics, thanks to this idea that I can tweak each marginal separately. Every topic has its own distribution. Okay, so that's the mean field family, but of course it's not yet fully specified. We need to understand what these parameters are, and we're going to assert that each factor is in the same family as the model's complete conditional. So if the complete conditional of beta given z and x is a Gaussian, then Q of beta given lambda is a Gaussian with free parameters lambda. Okay? Okay, so now everything is completely specified, and we can optimize the elbow. The elbow is a function of lambda and phi, and traditional variational inference uses coordinate ascent. It has a bank of variational parameters, and it iteratively optimizes each one, holding all the other ones fixed. And what you can show when you work out all this math is that doing coordinate ascent variational inference amounts to this. Set lambda star equal to the expected value of the natural parameter of the complete conditional, and then set phi star equal to its expected value of the natural parameter of the complete conditional. Remember, the complete conditional natural parameters are functions of these other hidden variables. We can take expectations of them with respect to Q. That's holding everything else fixed because of the mean field assumption. And so this gives us a coordinate ascent algorithm that marches uphill in the KL divergence, or downhill in the KL divergence, uphill in the elbow, by iteratively optimizing each parameter. All right, notice if you are interested in Gibbs sampling, the relationship to Gibbs sampling, right? Gibbs sampling iteratively samples from these complete conditionals. Here we iteratively set these parameters equal to something related to the same complete conditionals. And again, I emphasize the elbow is not convex. So this is going to go uphill. It's going to find a local optimum. So let's get back to the example. Here's the LDA graphical model. The local variables are the per document variables, okay? The colored buttons and the topic proportions. So these are the locals in our family of models. The global variables are, of course, the topics, the distributions over terms. All right, now here is the mean field variational distribution for that model. Everybody gets its own distribution. Every topic has its own distribution. Every document's topic proportions has its own distribution. Every word in every document has a colored button, and it has its own distribution phi. In this case, a categorical distribution over k elements. Okay, and so we can just run that algorithm that I explained, and you take this article that we saw from the beginning. We ask for 100. So what we did here was we took a collection of 17,000 articles with this first algorithm. That's a big collection, and asked for 100 topics. Okay, then we took this article. We did variational posterior inference with this article to get its posterior of its topic proportions, and here's the picture of those topic proportions. Right, this is running variational inference and then calculating the posterior topic proportions. And you can see that even though there's 100 topics, only a handful of them are somehow activated. And we can look at the most frequent words from the most frequent topics for this article. And you see things like genetics, evolutionary biology, diseases and survival, and data analysis. Okay, so in other words, positing the model using variational inference gives us this meaningful hidden structure through the posterior distribution of a model. Okay, and so this is classical variational inference. Now, this is like describes 25 papers from the 90s and 2000s, which each did this for a different model. Okay, the input is a data and a model. Initialize your variational parameters randomly. First, set each local parameter to its optimum. Then set the global parameter. Here I'm using that conjugacy result. And you repeat until the elbow has converged. I emphasize that this class of models has many, many models under it. Okay, so now you can use this algorithm for all those models. The problem is that it's inefficient, right? And let's go back to the algorithm. For each data point, so let's take topic modeling as an example. I initialize my topics randomly, so at first the topics mean nothing, right? I have 20,000 articles, the topics don't mean anything. And now I go through each article and I painstakingly figure out how it represents those topics, those garbage topics that I started out with. Okay, so I march through all 20,000 articles, understanding how it represents those topics, and then I update the topics to something hopefully more meaningful and repeat. Now, this is inefficient because we have to do local computation for each data point at each iteration, and then aggregate them to re-estimate the global structure. And so this can't handle massive data set. I had 17,000 articles, which is small. If I had millions of articles, then that first step would be painstaking. And again, the topics are meaningless anyway. It doesn't make sense to go through them all. And so the way to scale variational inference up to massive data is with stochastic variational inference.
Question?
Yeah.
You mentioned several special cases. Is this convex for some of those special cases, the elbow objective?
I'm not sure. Yeah. It's not even a conjecture because I'm just kind of guessing, but I imagine that maybe it's convex when exact inference is possible anyway, but I'd have to think more about it. Yeah. Okay, so how are we going to scale this up? Stochastic variational inference has this computational flow. I've got a massive data set. I've got a model that I'm trying to do approximate posterior inference on. I'm going to subsample some data from that massive data set. I'm going to infer the local structure of that subsampled data. And then I'm going to update my idea of the global structure from that local structure and repeat. Okay, and you can see I'm avoiding this problematic piece of marching through my massive data set at each iteration. And this is going to get us much faster estimates of the posterior. Okay. How many of you are not familiar with stochastic optimization? Good. That is nobody. So, stochastic optimization, I will make up more time and review it very quickly. Herb Robbins, invented by Herb Robbins and Monroe in like 1951. And the idea is simple. Replace the gradient with cheaper, noisy estimates of the gradient. Okay? I'm trying to march up a hill, and even if I don't know exactly where to go, if I have noisy estimates of where to go, I can repeatedly march up those noisy estimates, and eventually I'll get to the top of the hill. All right, this is guaranteed to converge to a local optimum when we have these kinds of non-convex objective functions like we do today. And this algorithm, 60 whatever years old, has enabled modern machine learning. Okay, without stochastic optimization, none of the things that machine learning is doing here and around us in a big radius would be possible. Okay, that's really, this idea is letting us scale everything up. Robbins. So, formally, we have noisy gradients. I'm going to denote those gradient hat of an objective function L. And what I'm going to do is I'm going to march with some step size rho t according to that noisy gradient. So what does this require for it to work? Well, since all of you are familiar, you all know, it requires unbiased gradients. That means that even though this is a noisy gradient, if I were to take the expectation of that noisy gradient, I would get the exact gradient. So that's unbiasedness. And it requires that the step size sequence rho t follows what's called the Robin-Monroe conditions, which in plain English say that I'm conservative enough that I'll get to the top, but I'm not so conservative that I can't reach anywhere. Okay? And so there are these conditions on rho t. So for the elbow, there's something called the natural gradient, all right, which is a type of gradient that's appropriate for probability distributions. And the natural gradient of the elbow, of the global variables, looks like this. Okay, again, I'm appealing to that conjugacy result. It's alpha plus a sum of expected sufficient statistics for these local terms minus the parameter itself. Okay? And these expected sufficient statistics are taken under the optimal local variational parameters for that sufficient statistic. So what I'm going to do is construct a noisy natural gradient very simply. I'm going to subsample from my data, get one data point uniformly at random, j. And then I'm going to calculate this scaled natural gradient. All right, this is a typical vanilla application of stochastic optimization at this point, where I'm subsampling data and then scaling my gradient appropriately. It's a good noisy gradient. Its expectation is the exact gradient. It's unbiased, and it only depends on the optimized parameter of one data point, okay, which means it's cheap. Okay, so I grab one document, see how it exhibits the topics, scale it, and then change my topics according to that one document. Okay, so now here's stochastic variational inference. My input is the data and the model. Again, I initialize my variational parameters randomly. I set my step sizes appropriately, and I repeat forever. I sample a document. I set its local parameter. I set what's called the intermediate global parameter, okay, which is basically this scaled natural gradient. And then I update my global parameter according to that scaled stochastic natural gradient. All right, and this has this exact computational flow, right? Grab a data point, look at its local structure, that's calculating the local variational parameters, update the global structure, that's moving the global variational parameters a little bit in the direction of the way that the local and the data pointed us to. Yeah?
I had a question on the previous slide. Does that P of t change over time? Or is it...
In the classical setup, yes. So the classical setup, the sum of the squares of rho t has to be less than infinity, but the sum of rho t has to diverge. That's this, I can get anywhere, but I'm conservative enough that I can get to the top. Although, you know, that's 1951. You keep going, and now constant learning rates and adaptive learning rates, and there's all kinds of stuff around the learning rates that we've been looking at, and also helps in this setting. But here, this is just the vanilla. Yeah. Okay. Good. Okay, so I mean, I already used LDA as the example. I sample a document, I estimate its local variational parameters using the current topics, form intermediate topics, and then update the topics. Okay, and why is this good? So here's a graph. So we're analyzing Wikipedia here. Okay, for whatever reason, we're fitting a topic model to Wikipedia, and in the x-axis is the number of documents that I've seen at the log scale. Okay, so this is how much computation I've done at the log scale. And the y-axis is perplexity. You can think of it just as an assessment of model fitness. How good is my model? Where lower numbers are better. Okay, so let's start with classical 1999 variational inference. We march through all the we start out with garbage topics. We then analyze every document in Wikipedia according to those garbage topics. We can handle about 100,000 with the classical algorithm. And we get our first set of topics, and then we evaluate them. Okay, and that gives us this point. Then we march through 100,000 documents again. Remember, it's at the log scale. And we get this point. And we get better and better and better each time. Okay, that's classical variational inference. But with stochastic variational inference, look at this green line, I can handle all 3.5 million documents, in theory, anyway. I mean, not in practice too, but I can imagine the corpus contains all of them, even though I haven't analyzed all of them at any point up to 3.3 million. And at each iteration, I grab a document or a little subset of documents, I update the topics, I immediately start doing better and better, so that by the time I've done as much calculation as I've done for the classical algorithm, I already have a much better idea of what the topics are. Okay, so this pays dividends in this case. There's a tiny bit of extra computation for the stochastic case, but it's essentially lined up here with number of documents. Okay, and as you see more and more, you get to a better and better fit, and in fact, you get a better fit than the batch algorithm gives you. It's interesting, but with stochastic optimization, even with the same population of documents that we're using for the batch algorithm, for the classical algorithm, we still get to a better model. Machine learners have seen this across problems, that using stochastic optimization to fit a non-convex objective function gets you to a better place than using something like coordinate-wise optimization. And Leon Botou has some interesting theories about why that's the case. Okay, and that's how I got this picture. All right, so in 2001, when Mike and Andrew and I were working on this, we never would have been able to analyze this many documents, but thanks to stochastic optimization, we can. Okay, and that's how I got this picture and this picture. And as I mentioned, now you can scale up many, many different models. So one exception is time series models. These are not technically in that class of models that I described, although Emily Fox has great work on how to scale up time series models using stochastic variational inference.
David?
Yeah.
Is there any effect of choosing a better unbiased estimator, or we have
Choosing a biased estimator?
a better unbiased estimator?
Ah. It depends on what you mean by better. But so we'll talk about this in the next part of the talk. There's bias and there's variance. And so often there's this trade-off that we can pay more to get lower variance gradient, and that can help. There's also work, again, this is from between 1951 and now, on thinking about biased gradients, right? So we know in statistics that in statistics, we used to only care about unbiased estimators of things, but then it started looking good when we sacrificed some bias for a large reduction in variance, and I think the same is happening in stochastic optimization too. So looking at biased gradients, like using things like annealing and things like that, and other ideas like that, we can do better, yeah. And the variance of the stochastic gradient is going to play a big role in the second part of the talk. Well, it won't play a big role in the talk, but it's important to deal with in this, what I'm going to describe next. Yeah. Other questions? Okay, so that was one way to use stochastic optimization to help us do approximate posterior inference. Now I want to talk about something called black box variational inference, which is a variation of the same theme. It's another way to use stochastic optimization to give us more power to variational inference. All right, and the idea is Monte Carlo gradients. Okay, so Monte Carlo gradients enable black box variational inference, by which I mean algorithms that efficiently perform Bayesian computation in any model. I'm in charge of the time, right? Okay, that's great. No, that's good. So I'm in charge of the time today. So I'm going to give myself 5 more minutes. Here's the thing. So I gave you this nice picture. So intuitive, and we want to scale things up, but we also want to make things generic. So one issue with this picture that the picture does not reveal is that going from your scientist collaborator at the whiteboard to an algorithm for calculating her posterior distribution can take a long time, can take years and months. And this is especially true for models that are not conditionally conjugate. So in the first half of the talk, we made some progress by setting up these conditional conjugacy assumptions and showing that it's a pretty big class of models that they capture. But there's actually lots of models that are not in that set. And for those models, it's especially hard to develop algorithms. And some examples are discrete choice models, which are common in economics and in political science, Bayesian generalized linear models, even logistic regression, I'll show you in a bit. So the idea behind black box variational inference, the goal, is to be able to easily use variational inference with any model. Okay, so if you're familiar with MCMC, it's kind of like we're trying to come up with the Metropolis Hastings of variational inference, the thing that we can use on everything. Our goal is that there are no exponential family requirements, so I don't have any requirements on the complete conditionals or the priors or the likelihoods, and that there's no mathematical work beyond specifying the model. Once you draw your graphical model and identify what each of those arrows are, we don't want you to have to do any more mathematical work. Okay, and the way it works is we sample from Q, so we have an estimate of the variational distribution, and we sample from it, or a related distribution. We form noisy gradients then, without doing any model-specific computation, calculation, and then use stochastic optimization. So somehow this sample from Q is going to get us to a noisy gradient of the elbow. I think, do you have a question, or just Arm? You have a question.
So you can't guarantee that your gradients are unbiased then?
Our gradients are going to be unbiased. Yeah, I'll show you. Yep. Okay, so I had that list before. Here's the list of a sampling of non-conjugate models. Really, any model if you dream of a model on the beach without any kind of constraints, you're going to come up with a non-conjugate model, I think. So nonlinear time series models, deep latent Gaussian models, models with attention, but like I mentioned, Bayesian generalized linear models, stochastic volatility models from finance, sigmoid belief networks, correlated topic models. A small variant of LDA suddenly becomes non-conjugate. Something called deep exponential families, which we've worked on, a way of doing deep learning in the context of probabilistic models, Bayesian neural networks, and so on. These are all examples of models that don't enjoy those complete conditionals being in the exponential family. Okay, and one simple one, as I mentioned, is logistic regression, Bayesian logistic regression. It should be the simplest model, but it's not. So, imagine, I'm going to just show you why this is hard. The data are pairs, xi, yi, where xi is a single covariate, a single feature, and yi is a binary label, and z here are the regression coefficients, okay? And so the model is that we have a Gaussian prior on the regression coefficient, and then y given x is a Bernoulli whose parameter is the sigmoid applied to z times x, okay? This is a one-feature logistic regression model. Now, let's make it even easier. We only have one data point, okay? So you see one binary label and one feature, all right? And the goal is to take this data point and condition on it and approximate the posterior coefficient, P of z given x and y. So the variational family Q of z, let's make it a normal. We had a normal prior on z. Let's make the variational family normal. And it, of course, has parameters mu and sigma squared, a mean and a variance. So here's the elbow. Okay, it's the expected log P of z minus log Q of z plus log P of y given x and z. This is another way to write the elbow. I just took the chain rule here on the joint, and then here's the entropy. And if I write that out, I get this expression. But of course, I have this, and I can take the expectations of a bunch of the terms, right? And here I've taken those expectations analytically with respect to the variational distribution. That's why you see the variational parameters appearing here. But then I have this term, expectation log 1 plus x xz. Okay, and I can't take that expectation analytically. All right, and we're stuck. Okay, so if we can't calculate the elbow, we can't optimize it. So what are some options? Well, over the years, researchers have come up with several. One is to derive a model-specific bound. Okay, so this is Mike Jordan and Tommy Yakula in the early days of variational inference worked with this in 1996. Michael Braun and John McAuliffe adapted it to discrete choice models in 2008. There have been other papers too. Okay, so these are model-specific bounds, meaning I've got this model, I know I care about it, I'm going to work hard to approximate the elbow for this model and optimize that approximation. And another approach is to use other approximations that are more generic but still require model-specific analysis. Okay, so I worked on this with a student, Chong Wang, in 2013. Knowles and Minka's paper is another instance of this type of approach to non-conjugacy. Okay, but neither satisfies our criteria for generic inference, right? These both require that you sit down with your model and do a little bit of work. So what's the key idea? The key idea and this will get to your biasness question, is to write the gradient as an expectation. Okay? And so this is called the score gradient. Okay? So if you download some papers about variational inference in NIPS and ICML, sometimes you're going to see the score gradient right now. And the score gradient looks like this. It's an expectation with respect to Q of a product of two terms. This term here, log p of x and z minus log q of z, I call that the instantaneous elbow. Okay, so this is like the elbow at z. Okay, times derivative with respect to new log q, which is called the score function. Okay, so this gives us, you can show in a few lines of algebra, this is a valid, not a valid, this is the gradient of the elbow. Okay? It's been invented several times. It's sometimes called the likelihood ratio or reinforced gradient. There's some old and new citations here. Now, once you have the gradient as an expectation with respect to Q, you can construct noisy unbiased estimates using Monte Carlo. Right? You just sample from Q and then take those samples and calculate a Monte Carlo estimate of that gradient. All right? And this satisfies these black box criteria. There's no model-specific analysis needed because all I need to evaluate this is I need to know the score function. Okay, but that's a property of the variational approximation. I can store that in a library and use it over and over again in many different models. And I need to evaluate log p of x and zs, but that's just writing down the model. If you have to be able to evaluate that. Well, that's not true. There's a whole other subfield of likelihood-free inference. But in many models, writing down the model means you can calculate this log joint. And you need to be able to calculate log q, the density of the variational approximation, which again doesn't have to do with the model. Okay, so this satisfies these black box criteria. And here's the algorithm. It's just stochastic optimization using stochastic gradients as defined by those Monte Carlo approximations. Okay. Here's just some examples of things you would store in a library that you could then reuse across models. Here's the score function, here's the log density, and here are different types of latent variables that you might employ in your model.
What's the form of a model-dependent term?
What's that?
What's the form
of this, log p of x and z? That's just the joint distribution. So you write down in logistic regression, it's just the log probability of the data given a realization of the hidden variables. So that's often easy to calculate. It's just when you need to marginalize things out that it's difficult. Okay, so, but this speaks to your question earlier, Moses, that this doesn't work out of the box. Okay, so you have to control the variance of this gradient. That's the variance of that simple gradient is going to be much too large for it to be useful. You have to have such a small learning rate that it takes forever to fit. And so in our paper about this, we have a bunch of different tools that we use to keep unbiasedness but reduce the variance. Things like Rao-Black equalization and control variance. And then subsequent work by others has used things like importance sampling and other techniques to lower the variance of these gradients. Here too, we use adaptive learning rates, these more elaborate learning rates that aren't simply the Robbins-Monroe learning rates, but things like the Adagrad and others, RMS prop, to manage the optimization. And you know, even though, so we're doing Monte Carlo estimation here, but we can subsample the data within that and do stochastic variational inference inside black box variational inference to scale this up. Okay, so this is score gradient black box variational inference. And we, for example, have used this to fit these kind of complex, deep exponential families. I'm out of time, I won't go into what this is, but it's basically an adaptation of deep representations to probability models where Radford Neal really wrote down this model in 1990, but what flummoxed us until now was how to do inference in this model. You could only do it with a couple types of distributions here, sigmoid belief nets with model-specific ways of handling the non-conjugacy. But now with black box variational inference, for example, you can fit these kinds of models with many different types of priors and assumptions inside these layers. This is how we did this, what's called topographic factor analysis for fMRI data. Here, what the neuroscientists wanted just did not line up with complete conditionals being in the exponential family as much as we were trying to strong-arm him into doing that. And so we worked on we used black box variational inference to fit this complicated model. And black box variational inference is what lets us now take variational inference and use it in probabilistic programming. Okay, so in one sentence, probabilistic programming is exactly what it sounds like. Okay, so in probabilistic programming, what happens, in regular programming, you write a program and you compile that program down into an executable that runs the program. In probabilistic programming, you write a model down as a program, right? We describe LDA almost as a program that generates data. You can write your favorite model down, or model you just made up today, as a program that generates data. And then, instead of compiling that into an executable that generates data, compile it into an executable that takes data as input and spits out inferences. Okay, it's a very natural idea of what we would want out of a system that helps us automate inference. But of course, the rub is that probabilistic programming requires methods of deriving inference algorithms from programs, i.e. probabilistic programming compilers. And these kinds of ideas, black box variational inference, enable that. So for example, we have a variant of this type of algorithm now implemented in the STAN programming system that lets you run variational inference with a model you wrote down without having to do any work at all, except for writing the model. Okay, and again, here's another collection of non-conjugate models. Okay, so I wanted this to be a tutorial about modern VI, and there are two ideas that were left on the table. So I want to just very quickly describe them so that you're primed when you read about them more carefully. You can maybe understand something more. Okay, and those two ideas are the reparameterization gradient and amortized inference. So I described stochastic inference and black box inference. The reparameterization gradient is another way to express the gradient of the elbow as a expectation and use Monte Carlo, but it uses transformations. Okay, so the idea in the reparameterization gradient is that I write my latent variable down as a transformed latent variable, for example, a transformed Gaussian. And if I can do that, and if log p of x and z is differentiable with respect to z, with respect to the latent variables, then I can write my gradient this way. Okay, so this is a expectation with respect to a alternative distribution of the derivative of the instantaneous gradient with respect to the latent variable itself, times the derivative with respect to the variational parameter of the way that we transform the hidden variable into this transformed variable that we're taking the expectation with respect to. The key idea is that this expectation does not depend on the variational parameters. That's what's nice. And so then this makes it easy to, then using Monte Carlo here is very efficient and good. So that's one idea that you'll see. Another idea that you'll see is called amortization. This is the key idea behind what's called the variational autoencoder. And it's also very simple. Amortization simply says that the variational parameters are a function of the input. Okay, so in this entire talk, the variational parameters were these free knobs that we could turn. But we can imagine modeling the variational parameters themselves. We can make them a function of the input that we have taken in that we are trying to calculate the variational parameters of. And the advantage there is that when working on future data, you can get fast estimates of their variational parameters without having to run another optimization. Okay, and this is the variational autoencoder is an instance of this, where the model is a deep neural network plus Gaussian noise, and the variational parameters are also a deep neural network. Okay, so I know maybe it was even a mistake to show these two slides, but I just wanted to mention the reparameterization gradient is one where you transform the latent variable, and this gives you some advantages in terms of the resulting Monte Carlo estimates of the gradient of the elbow. And amortization is simply a way to generalize variational parameters so that you can do better in the future, or at least faster. Okay? Good. So this is the picture I showed you a few times. Posterior inference is the key algorithmic problem. It answers the question, what does my model say about my data? And hopefully I've convinced you that our goal in machine learning is to make posterior inference general to many, many models and scalable to very large data sets. Okay? Variational inference turns that calculation of the posterior into an optimization problem. And stochastic optimization helps us take this path for many models automatically, for massive data sets, and in an amortized way to speed up future calculations. Okay, so my student Dustin Tran has developed a probabilistic programming library called Edward for playing with these ideas. I encourage you to take a look at it if you're interested. And here is just a short list of some open problems in variational inference that I think are interesting in terms of what is needed. And I'm totally out of time, but I'll just mention a couple things. One is theory, one is better optimization, one is alternative divergences, and one is better approximations. And if you're interested in talking about any of these, either now or at the break, I'm happy to. Thanks very much.
We have to break now, so please ask all kinds of questions in the break. We'll meet again at 11.
Sorry, Santosh, I took a little too long. Yeah.
Yeah. You computer? Yes, they're here.